and welcome back to another fun and exciting tutorial brought to you by Expert Guides YouTube channel. Before we begin, let me introduce myself first. My name is Joan Shaira S. Malicana. I am currently taking my graduate studies at the University of the Philippines, Diliman, taking up Master of Arts in Education with specialization in Chemistry Education. I took my bachelor's degree at the Philippine Normal University, Manila, with a degree on Bachelor of Science in Chemistry for Teachers. Now, I am a chemistry and a research teacher at a public science high school since 2016. And with that, as a research advisor, I am proud that we have won different division, regional, and national research competitions. All right, let's begin our discussion for today. You've probably heard the word atom, but what exactly is atom and what do we know from it? To tell you, let's first look at the amazing things in our universe. When we humans look at the universe around us from a scale like things in the cosmos, like stars, one example is the sun, all the way down to a more human scale like these cute pets, and all the way down to the microscopic scale, which is a visualization of a coronavirus, it seems like there's infinite number of things out there. But here's an interesting question. Have you ever wondered what is the smallest matter? To answer this, a perfect scenario would be if you were to chop or cut a matter, an apple for instance, you could just chop forever and ever like there was no end to smallness. This is where Democritus came in, an ancient Greek philosopher. He insisted that at some point you would reach particles so small and so indestructible they could not be divided any further. He called them atomos or atoms, which means uncuttable or indivisible. Matter itself is made of a collection of different types of atoms, such as this sugar, having carbon atoms, hydrogen atoms, and oxygen atoms. But what is the definition of atom? On the basis of Dalton's atomic theory, we can define an atom as the basic unit of an element that can enter into chemical combination. To this date, scientists have discovered 118 kinds of atoms, which we call elements. You can find them presented in a chart called the periodic table of elements. All things are made up of atom. But a single atom is so small it is impossible to see with the naked eye. In fact, a human hair is roughly 500 times wider than an atom. Just take a look in your screen, how small this is. But what if I tell you that this very small particle actually possesses internal structure? Imagine there are still smaller things than it, which means they are made up of even smaller particles, which are called subatomic particles. Because of the series of investigations by our scientists, this had led to the discovery of three such particles, such as electrons, protons, and neutrons. Now, let's look at the insides of an atom. Here's a sample representation of a structure of an atom, wherein at the centermost part of it, we can find the nucleus. If we're going to imagine the size of a nucleus, let's expand the size of an atom to that of this sports stadium. When compared, the nucleus would just be the size of a marble. Imagine how small the nucleus is. Well, ironically, most of the mass of an atom comes from the nucleus. Now, inside the nucleus, we have one subatomic particle, which is protons. And protons are tiny, dense region at the center of the atom, and they have a positive charge. They also have 1 AMU or atomic mass unit, which is equivalent to 1.67 times 10 raised to negative 24 grams. Together with neutrons, protons and neutrons, they make up virtually all of the mass of an atom. Now, protons are also important since they give the identity of an atom. We'll further discuss that later. Alright, so another subatomic particle inside the nucleus is neutron. So atoms of all elements have neutrons inside the nucleus except for one element. Can you guess which element is that? You guessed that right. Correct. We have hydrogen. And some of the atoms of hydrogen do not have neutrons inside their nucleus. Now, neutrons, unlike protons and electrons, have no charge or neutral and are about the same mass somehow with the protons. Well, it's technically heavier, somehow heavier with protons. But they still given same 1 AMU or 1 atomic mass unit with equivalent to 1.6749 times 10 raised to negative 24 grams. So the neutrons here, we can see that neutrons stands for n raised to 0 or the 0 stands for 0 charge. Now, looking at the outside of the nucleus, we can find electrons. So electrons have an electric charge of negative 1 or have negatively charged particles and are the same numbers with protons of an atom. What is the meaning of this? It means that all atoms have the same electrons, number of electrons and protons. But take note, we're talking about neutral atoms here, meaning the positive and the negative charges have cancelled out. They are equivalent to 0. So electrons are very small, that the mass of an electron is only about 1 over 2,000 the mass of a proton or neutron. So technically, they do not contribute virtually to the total mass of an atom. So if we're talking about the mass of an atom, we're just going to look at the nucleus, okay? Which is the protons and the neutrons. So because opposite electric charges attract one another, okay, so we're talking about here the positive and the negative. So the negative electrons here, okay, the negative electrons are attracted to the positive nucleus here at the center. So this force of attraction keeps the electron constantly moving through the otherwise empty space around the nucleus. So this figure is actually a common way to represent the structure of an atom. Well, it shows here that the electrons as a particle orbiting the nucleus is similar to the way the planets orbit the sun. However, take note of this. This is an incorrect perspective. Why? Because quantum mechanics demonstrates that electrons are more complicated, meaning electrons travel around the nucleus in orbitals. So we can see here the orbitals here and here. Now, orbitals are areas, these are areas within the atoms where there is a high probability of finding the electrons. Since we are still not sure and it is very impossible to know both the speed and the location of an electron at the same time. Well, this phenomenon is known as the Heisenberg's uncertainty principle and is a famous result of quantum mechanics. So technically, we cannot predict actually the location and the speed of an electron. To sum it up, we can see in the table that the proton has a symbol of p raised to positive and has a mass of 1.67 times 10 raised to negative 24 and also has a charge unit of positive 1 is located inside the nucleus. Whereas the neutron, with a symbol of n raised to 0 and has a slightly higher mass than the proton, has a charge unit of 0 and location is inside the nucleus. Lastly, the electron, with the symbol of e raised to negative and has a mass of 9.10 times 10 raised to negative 28 and has a charge unit of negative 1, can be found outside the nucleus. Isn't it very easy? Now, the identity of an atom relies on its number of proton and the number of neutron. Let's first discuss the number of protons using the atomic number. Atomic number is represented by Ze or Zahl, meaning numbers in Germany, and it is the number of protons in the nucleus of each atom of an element. Now, you have to imagine that we are in a neutral atom. So in a neutral atom, the number of protons, P plus, is equal to the number of electrons, E negative. But what exactly are neutral atoms? Now, take note that negative and positive charges of equal magnitude cancel each other out. So this means that the negative charge on an electron perfectly balances the positive charge on the proton. In other words, a neutral atom must have exactly one electron for every proton. Example, if an atom has one proton, it must have one electron. Another example, if a neutral atom, take note always, it must be a neutral atom. If a neutral atom has 10 protons, it must have 10 electrons. Get it? It's very easy, right? Let's have this fluorine. So basically, the chemical identity of an atom can be determined solely from its atomic number. That's why this atomic number is very important. So in a periodic table, we can see that fluorine, with a chemical symbol of F, has an atomic number of 9. This only means that each fluorine atom has 9 protons and 9 electrons. Or viewed another way, every atom in the universe that contains 9 protons is correctly named fluorine. Another example, let's have iron. So we can see here, the subscript is 26, meaning its atomic number is 26. Therefore, iron has 26 protons and 26 electrons. Whereas lead, having atomic number which is 82, okay? Lead has 82 protons and 82 electrons. Very easy. Very good. You are catching up. Now, let's proceed to the mass of an atom. Now, the mass of an atom is computed through the mass number, which is represented by A or Atomgewicht, which means atomic weight in Germany. And a mass number is the total number of protons and neutrons in the nucleus of an atom. So going back from our discussion previously, that the mass of an atom can be only found from inside the nucleus. So inside the nucleus, we only have two subatomic particles, which are the proton and neutron, thereby giving that the mass number is equal to the number of protons plus the number of neutrons. So since the number of protons is equal to its atomic number, which is Z, we can also write it here that the mass number is atomic number plus the number of neutrons. Let's have chlorine as an example. So here, again, the subscript 17, meaning its atomic number is 17, concluding that the number of protons of chlorine is also 17. Very good. But we have a given here, which is the number of neutrons is equal to 18. So let's try to compute for the mass number. So since the mass number is just summing protons and neutrons, okay, again, mass number is equal to protons plus neutrons, substituting the values of the chlorine, wherein its protons is 17 and its neutrons is 18, the mass number of chlorine would be 35. Okay, very easy. Okay, so now let's proceed to iron, same examples, and lead. Let's start with iron first. So again here, its atomic number is 26, thereby giving us the number of protons as 26. It's given the number of neutrons is 30, so computing for its mass number, proton plus neutrons, 26 plus 30 is equal to 56. So the total mass number of iron is 56. For the lead, Again, its atomic number is 82, and its number of protons is 82 as well. The number of neutrons that is given is 125. Looking for the mass number, we're in adding only the protons and neutrons, which is 82 plus 125. We have the total mass number of lead as 207. Very good. Now, the accepted way to denote the atomic number and the mass number of an atom of an element is as follows. So here X symbolizes an element symbol. Okay, and you have to keep in mind that Z here, the subscript is always the atomic number. Okay, the subscript here is the atomic number, and the superscript is the mass number. Now, the strategy here, guys, is the mass number is always greater than the atomic number. Okay? So now, what if we have atoms of a given element, of one element, but they do not have the same mass? We have isotopes. So isotopes are atoms with the same atomic number but different in mass number. So why do they have the same atomic number? Again, atomic number defines an element. So meaning atomic number is always one element. So when we're talking about, say, 9 atomic number, we are talking about only fluorine. Because if that is the different atomic number, that is a different element already. Get it? So since isotopes have same atomic number, of course, again, they have the same number of protons. But the only difference is that their number of neutrons. Because again, they have the different atomic mass, and atomic mass is equal to number of protons plus neutrons, and protons cannot be changed, okay, in the same element. So meaning the neutrons is the only one. That is the reason for the different mass number. Okay, so let's have this cobalt isotopes as an example. So we have here cobalt 59, which is a stable isotope of cobalt. It's not radioactive. And cobalt 60, which is extensively employed as a radiation source to arrest the development of cancer. So this time, let's identify the number of neutrons. So since we can see here that the atomic number is 27, the subscript, and the mass number is 59, the superscript. So again, atomic number is 27, mass number is 59. To get the number of neutrons, the formula would be number of neutrons is equal to mass number minus the number of protons. So since the mass number here is 59 minus the number of protons, which is 27, the number of neutrons here for cobalt 59 is equivalent to 32. While for cobalt 60, atomic number, again, they have the same atomic number, it's 27. And the mass number is 60 in this part of our cobalt 60 isotope. Looking for its number of neutrons, let's compute. So mass number minus number of protons. So 60 minus 27. The number of neutrons of cobalt 60 is 33. Now, we can see here different atoms, but with the same elements. But their chemical properties are actually, again, determined by protons and electrons. So, neutrons do not take part in chemical changes under normal conditions. So, neutrons do not actually provide an effect to the isotopes. Therefore, isotopes of the same element have similar chemistries, forming the same types of compounds and displaying similar reactivities. So now let's try to have a practice exercise. So again, I want you to remember that the superscript, okay, denotes the mass number A, and the subscript denotes the atomic number Z. Okay? And always keep in mind that the mass number is always greater than the atomic number. So let's try to have an example. So I want you to give the number of protons, neutrons, and electrons in each of the following species. So let's try the first three. Okay, so I'll be giving you how many minutes? You can pause this video, but let's proceed to the answer. So since we can see here that the sodium, okay, has an atomic number of 11 and a mass number of 20, okay, so here is Z is equal to 11, at mass number is 20. So since atomic number is equal to the number of protons, our number of protons here is 11. And since number of protons is equal to number of electrons, it's still also 11. So this time, we're going to compute only for the number of neutrons. So number of neutrons is equal to mass number minus atomic number. So 20 minus 11, we have the number of neutrons of sodium as 9. Okay, so we have sodium 20 with a number of neutrons of 9. So another example of a sodium, its isotope is sodium 22. Okay, so since they have the same number of protons or atomic number, which is 11, but differ in mass number, which is 22 in this example, the number of protons and the number of electrons is still the same. We have 11, but the number of neutrons when we are to compute, since it is 22, okay, mass number minus atomic number, which is 11, we have the number of neutrons of sodium 22 is 11. Okay? Now, let's try number 3. So we can see here, the only given is mass number. So how will you know the atomic number? So take a look at the periodic table, and when we see oxygen in the periodic table, we can find that its atomic number is equal to 8. Okay, so let's just copy here the atomic mass or the mass number. And then, since atomic number is 8, therefore, its number of protons is 8, and its number of electrons is also 8. But the number of neutrons, we have mass number minus atomic number. So we have 17 minus 8. The total number of neutrons of an oxygen is equal to 9. All right, so I have more examples here. Okay, let's have carbon 14. So carbon 14 can also be represented as 14C. So again, the 14 is at its superscript. So therefore, 14 here is the mass number. So in order to find for its atomic number, we have to look at the periodic table, okay? And in the periodic table, carbon is 6, okay? Its atomic number is 6. So we can now conclude that the proton of carbon is 6 and its number of electrons is also 6. But the number of neutrons, when we are to compute, we have to substitute 14 minus 6, therefore giving us the number of neutrons is 8. Now, last example. Copper, 63. So copper 63, again, the atomic number was not given, so you have to take a look at the periodic table. And the atomic mass is only given, which is 63. So atomic number here, which is 29, okay? So meaning that our number of protons is 29, and our number of electrons is also 29. So when we are to compute for the number of neutrons, so we have mass number minus atomic number, 63 minus 29, a total of number of neutrons as 34 for copper 63. Okay, you are getting good at this. For our next topic, we will be discussing about molecules, and you can check out Expert Guides tutorial services. Also, do not forget to subscribe to our YouTube channel, Expert Guides Tutorial Services, to have a sneak peek of other lectures. I'll see you and goodbye!